Greetings, chemistry students. Today, I'm going to show you the last thing we're going to learn as a part of this unit, which is going to kind of wrap up gases and heat. Today, after this, you're going to have a worksheet that I already gave you in class, so you've already seen it, but I'll upload a copy of it to Google Classroom for you to work on from there if you prefer, which is going to cover heat. But this is what's called a phase diagram. And what it shows is a graph of pressure versus temperature. And it shows where you have solid, liquid, and vapor or gas present. And if we're talking about normal conditions, that is at 1 atmosphere. And so this shows on the phase diagram for water that at 1 atmosphere, as you increase the temperature, when you hit 0 degrees Celsius, you transition from a solid to a liquid. And then when you hit 100 degrees Celsius, you transition from a liquid to a vapor. Now, I showed you in a demonstration before that you can essentially boil water by lowering the atmospheric pressure and causing it to boil when I did that inside of a syringe. And that's where you can take liquid water in between its freezing and boiling point, and you lower the pressure. And as you transition from liquid to vapor, that's vaporization right there as you cross this blue line right here. So that would become vaporization or boiling that way. You can have sublimation if you go from a solid to a gas in this region. And as you cross this red line right here, if you cross this red line going one way or the other, that's melting or freezing, depending on whether you're heating it up or cooling it down. You can also, interestingly, for ice, if you increase the pressure, it actually melts. Water is fairly unique in having this negative slope for this line right here, whereas you increase the pressure, ice melts, which is why when you have ice skating, the skates apply a lot of pressure to the ice and actually melt it, creating liquid ice underneath, which helps to lubricate the skates as they go across. Now, there are 2 unique points you should be able to identify on a phase diagram. The first is this point right here called the triple point. This is the only point where you can have solid, liquid, and vapor all coexist with no net change. So at that very specific temperature and pressure, you could have solid ice, liquid water, and water vapor, and you won't have the ice melting or the liquid freezing or evaporating. Everything just kind of stays how it is. It's called equilibrium. And then there's this other point called the critical point, where beyond that, liquid and vapor become indistinguishable. In other words, the liquid phase really ceases to exist past that point. And you end up with what's called a supercritical fluid. Now, this is getting to some pretty extreme conditions. That's a fairly high temperature, and it's a really high pressure up here at the critical point. Now, supercritical carbon dioxide, once you get up here, 31 degrees Celsius, 73 atmospheres, that's not too horribly extreme. That's a little above room temperature, but fairly high pressure. And supercritical carbon dioxide actually has quite a few uses. It will dissolve caffeine, so they can use that process to decaffeinate coffee beans. They also use it for dry cleaning. Now, this phase diagram for carbon dioxide is pretty unique because at room temperature, we're somewhere right here where carbon dioxide is typically a gas. But under 1 atmosphere of pressure, if you have solid carbon dioxide, it sublimates directly. Liquid carbon dioxide cannot exist at a pressure below 5 atmospheres. So 5 times the pressure in this room is what you would have to have in order for liquid carbon dioxide to exist, which is why it's called dry ice, because it just directly sublimates.